Okay, um, now we'll look at triple integrals. Now, these are going to be in 4 dimensions, so we can't picture them. It doesn't represent volume in general. So, its volume's in 3 dimensions. We say hypervolume in 4 dimensions. Okay, we'll take F continuous of a rectangular box. And we'll just take the axis to be general, Z, Y axis, normal. So this is from Z to D. This will be from A to B. The X's and the Z's are from, say, E to F. So we're just going to integrate A to B, C to D, B to F, F, X, Y, Z, dx, dy, dz. Now, there's different cases. Case 1, we'll say that in the, say, xy plane, we'll have a region like this. Let's get away from the rectangular box. And this is the x and y axis. But when we move to 3 dimensions, okay, we'll say from A to B, and we have these functions. Say this is f of x and g of x. And when we translate that, move it up into 3 space, we have this function, and it's not going to be over a box anymore. What we're going to do is integrate over this 3-dimensional object. Right here, that's what we're going to integrate over instead of R. So this time, our region is R, and this is K of X, Y. And let's say that is J, that surface is J of X, Y. So in that case, we're going to integrate from J to K, and then from F to G, and then from A to B. dz, dy, dx. Now notice, this is always going to be true. Again, that's not the volume of this region R. That region R is what we're integrating over, and F is our function. So we didn't even picture F in this example because it's 3 dimensions. We can't. So in the first integral, or actually the last one, you're integrating over constants, and this is going to be always true. These are going to always be functions of one variable, the second integration, and then the inside integration, it's a function of, at most, 2 variables. So it could be 1 variable, but it could also be 2 variables. All right, in another case, we could have this C to D, and our functions are like that, and this will be H of Y, I of Y, okay, and then again that translates up here should be this. K, and that's J, and this is our region R. So we're integrating over that region. This time we're going to be going from J to K. Okay, that's the same. Then we're going from H to I. Just check it. Okay. Okay. And then from C to D. So this order is Z, X, Y. Okay, then remember, when f of x, y was equal to 1, then the double integral RdA was equal to the area of the solid corresponding to R. Then, so this triple integral over a surface S dV equals the volume bounded by S when f of x, y, z is 1. So it does represent volume only when the function's 1. Okay, so let's do an example. I want the volume of the solid above the xy plane bounded by these two functions. Okay, let's use Maple to look at these. Okay, I want to plot these. I'm going to do with plots. I'm going to let P equal plot will be the first one. And let me go from -2 to 2, and y goes from -1 to 1. Okay, and then Q, let me do as an implicit plot because I don't have z equal to anything. And that's going to be x squared plus 4 times y squared equal 4. I'll go over the same region. X is from 2 to 2, y is -1 to 1, and z is, let's do 0 to 4. We can adjust it after we get our picture, and then I want to display on the same set of axes. Okay, I had spelled implicit wrong. So again, let's do with plots. We're going to plot the first one and the second one. Let me suppress the output. And then we're going to display both of them on the same. Okay, so that's better. So we have kind of a cylinder here, and then it has a U-shaped top or a bowl on top of it. And that's what the picture's going to look like. So let me box these. So when we spin it around, you can see that's the underside of it. So the solid, it's going to be filled in underneath there, and it's going to have a bowl cut out of it. So it's a solid cylinder with a bowl cut out of it, so it'd have a bowl-shaped top. I think you can see the picture pretty good. Okay, so I just wanted to get a feel for what our picture looks like. So, our z is going to be between the function and 0 because it's above the xy plane. We're going to solve the other one for y. Let's just do that. And then y is, again, positive because it's above the xy plane. So that'll be 4 minus x squared times a half. So y is going to be between that and 0. And our x is going to be between 2 and 0. So if you look at the picture, again, I'll try to draw it. Okay, the base is an ellipse, and this is 2, and this is negative 2. And then we have parabola shape, and that's coming up here. And it's going to be a bowl. And we want the solid in here, in the red. It's going to be all filled in. Okay. So our x, you see, is between 0 and 2. So we're going to integrate one, and z we're going to go between 0 and x plus 4y squared. Y is going to go from 0 to a half square root of 4 minus x squared, and 0 to 2. We're just going to do the first octant. I should have added that in here. Okay, we're going to use Maple to integrate that. So first, we're integrating 1 from z equals 0 to x squared plus 4 times y squared. Okay, then we're going to integrate that, where y goes from 0 to 1/2 square root 4 minus x squared say that's times, I forgot. And then we're going to integrate that. X goes from 0 to 2. So we get pi for an answer. Now, that's going to be the same as the double integral. Let me go back to here. Of the function. So that's going to go from 0 to 2, 0 to 1/2 square root of 4 minus x squared plus 4y squared dy dx. And you should be able to see why that's true, but anyway, we'll do it in Maple. And we're going to go from 0 to and we're going to say, I forgot, this is going to be y equal. And then we're going to integrate that. You can see it's the same already. X equals 0 to 2, and this is in the first octant. We get the same answers, pi. So Maple's real powerful, and it'll help us work these problems. Okay, we'll look at some of the example problems in your homework.